All right, concentration of solutions. There's going to be 3 kinds of concentrations that we're going to do. Molarity is by far the most common when we're talking about concentration. And it is defined as the moles of solute in liters of solution. And we will designate the unit by a big M, capital M. Okay? So when you see something that says it's 5.7 molar, I want you to be thinking that molar is the same as moles per liter, because we're going to use that as a conversion factor. Okay? And if you're not visualizing moles per liter, you'll just look at it and go, what do I do with this big M? Okay? So we're going to work a couple of problems. You'll have that. Oh, that's right. Y'all have to actually write that in the blank. That's why it's taking people so long today. I was like, it's right there, but it's not units. Okay, got it? All right, so our first problem says calculate the molarity of a solution prepared by dissolving 11.85 grams of potassium permanganate in 750 milliliters of water. So remember, molarity is moles over liter. So first thing we're going to need to do that is change that 750 milliliters to liters, which is 0.750, because we divide by 1,000 because there's 1,000 milliliters in a liter. So we're going to turn the grams of potassium permanganate into moles. So we have 11.85 grams of potassium permanganate, and we need moles, so we're going to use the molar mass. The molar mass of that is 158.04, and 1 mole. So now that we have moles, we have the top part that we need. So we got the moles, but we need the liters. And so we're going to say 1 over 0.75 liters because I need to divide by it, right? I need it on the bottom. Okay? So I'm going to throw all that in my trusty calculator. And I need 3 sig figs because of that 750 dot. So that my answer will be 0.100 molar KMNO4. Now, earlier today, this little step here was kind of confusing kids. They were like, why is there a 1 on top? It's because I need to divide by it. But if you don't like doing it that way, you can just convert to moles like you're used to. That would come out to 0.075 moles if I just did step 1 and step 2. And then I can say divided by 0.75 liters to get my moles per liter unit, and it comes out to the same thing. So either one of those ways is acceptable. Just some people like to just do it all at once and put it in the calculator all at once. Okay? Any question on what I did? Okay, so let's do some more examples. This is going to be on your next page where there's some practice problems, so turn your page. Okay? And then it should read, calculate the mass of NaCl in 175 milliliters. Is that what y'all's next one is? If you turn the page. Yeah. Yeah, there we go. So we have 175 milliliters of the 0.5 molar NaCl solution. Okay? And it wants to know, calculate the mass of NaCl that we need. Okay? So I want you to write this down because this is going to be important, especially when we get to solution stoichiometry. Volume times molarity equals moles of solute. So anytime someone gives you a volume and a molarity, you can get to moles because you multiply them. So start with molarity, 0.500 moles of NaCl per 1 liter. If I multiply by 0.175 liters, I get rid of liters. Now I'm in moles of sodium chloride. How can I get to grams? Molar mass. So 58.44 grams of sodium chloride over 1 mole. So now my moles cancel. And throw that in your calculator, 0.5 times 0.175 times 58.44, and I need 3 sig figs, so I get 5.11 grams of sodium chloride. So if I went into the lab and I massed out 5.11 grams of sodium chloride and I dissolved it in 175 milliliters of water, I would have a 0.5 molar solution.
How can you put that 1 liter 100 to 500 the 0.500 moles of things?
How can I put it under?
Yeah.
I don't put it under. I put it on top.
No, in the sugar.
For the bottom left.
Why did you put it there?
Here?
Yes.
Because molarity is moles per liter.
Okay.
Yeah. Remember I said, think of, when you see molarity, I want you to think moles per liter, because it's defined as moles of solute per liter of solution. So anytime you're doing calculations and you see big M, I want you to immediately write moles per liter, because you're going to use that to convert. Okay? So that was a good question. Your next example says calculate the volume in milliliters needed to prepare 2.48 molar of sodium hydroxide containing the 31.52 grams. Okay? So we want to know how much volume would we need to add to the 31.52 grams to make it be that molarity. So we're going to start with the 31.52 grams that we know we have of sodium hydroxide. I know that I'm going to need to be in moles because molarity is dealing with moles. So I'm going to divide by the molar mass, which is 40. So I got rid of grams. Now I want to get rid of moles and get to liters. What do I have at my disposal? Huh? Molarity. I have my molarity. So I'm going to take my molarity that they gave me of 2.48 moles of NaOH per liter of solution. And this is my abbreviation for solution. You can just put the liter. You don't have to put the solution. And this wants it in milliliters, so I'm going to say 1 liter is 1,000 milliliters. So I throw all that in my calculator, and I believe it came out to 318. I'm going by memory, so I could be wrong. So if I took my 31.52 grams of sodium hydroxide, massed that out, and added it to 318 milliliter of water, then my molarity would be 2.48. Okay? Yes, sir?
So it's saying, so we know that volume times molarity equals molar solute.
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 Uh-huh.
So 2.48 is the molarity, right?
Because that gave us that in the problem, yes. 2.48, big M is molarity.
So we could so it's basically volume times 2.48 equals 31.53 grams of,
If you worked it backwards, yeah. Yeah, if you worked it backwards. Okay? Or you could also say moles divided by molarity gives you liters, gives you volume.
yes.
You could turn that around, right? Because if you know this, right?
Yeah.
If I want volume, I'm going to say volume is moles divided by molarity, right?
Yeah.
So, okay. So that brings me to molality, which is in your little supplement because I messed up. Oh, wait, I just lied to you. We have to do concentration of ions, which is still in your packet. Sorry, I forgot that was next. So the way concentration of ions works is when you break apart, remember we're talking about net ionics, and when I dissolve an ionic compound, it breaks apart into its constituent ions. And so it does so like this right here, where I've got 3 sodium and 1 phosphate. So when you're dealing with concentration, you have to take into account those coefficients. So if I had calcium phosphide, okay, that's going to give me 3 Ca2 pluses plus 2 phosphides. So in terms of the molarity or the concentration, this is 0.25 of the whole thing, but when I dissociate it, I get 3 times as many calcium ions, because when it breaks apart, there's 3 of them. So the calcium ions concentration would actually be 0.75 molarity of calcium and 0.50 molar of phosphide. So that's the way that works. So whatever coefficient is here, you just multiply the molarity by it, and that's how many of the ion you would have. Okay? So let's do silver sulfite, which is Ag2SO3. When it breaks apart, it's going to give you 2 silver plus an sulfite, excuse me. And this is 0.33 molar. So how much silver would I have? 0.66 molar silver and 0.33 molar of sulfite. Because basically it takes twice as much silver to go with the sulfite. Okay? So that's pretty straightforward. Okay? Now we're going to the extra packet. Sorry about that. I forgot that this was in between.
Hers yet.
Okay.
Time, so.
Okay, you can get it tomorrow. Have a good day.
Yeah, you too.
Okay, now we're at molality. And molality, which looks just like molarity, except it's an L instead of an R, except I just spelled that wrong. Okay? And just to keep it nice and confusing, it's designated with a lowercase m. So on the test, you're going to need to be very careful. Am I giving you a big M or a little m? Okay? And so it is the same in terms of moles of solute is on the top, but on the bottom, instead of liters of solutions, it's kilogram of solvent. Kilogram of solvent. So just like when we were saying molarity, when you see that, think of moles per liter. When you see molality, I want you to think moles of kilogram. Moles over kilogram.
Maybe if like the lowercase m, you can think since that's the extra L, they have some sort of lowercase.
Whatever works for you to help you remember it.
I'm not gonna remember it.
Okay? So now let's work a couple of problems with molality. Okay? So, same concept, except now we're using kilograms. Okay? One thing that I need you to write down somewhere, because it's going to come in handy, is that the density of water is 1 gram per milliliter. So every 1 gram of water, every 1 milliliter weighs 1 gram or has a mass of 1 gram. So if I told you I had 800 grams of water, how many milliliters do I have? 800. It's equivalent, okay? That's going to come in handy because sometimes, honestly, most of the time when we go into the lab, I don't measure out grams of water. I pour it in a graduated cylinder and I do volume, okay? But volume, that's very handy that water is 1 because it's the same, okay? So this time I see that I have molality, calculate the molality. So that means I'm going to want moles over kilogram. So I have 750 grams of water. So that means I have 0.750 kilograms. Because grams are smaller than kilograms. So to divide by 1,000. Okay? So 15.54 grams of potassium hydroxide. I got to get rid of grams. So the molar mass is 56.11. So now I'm in moles, so now I can simply divide by my kilograms. Because then I would have moles and kilograms over each other, which is what I need. And it comes out to 0.369 molal is how you say it. It's a molal solution. Again, if you don't like this last step in the same problem, you could calculate the moles on its own and it would come out to 0.277 moles over 0.75 kilogram and it would give you the same answer. So some kids didn't like doing it here, they liked doing it like the second way. Either way is acceptable, whichever floats your boat. Are you raising, do you have a question?
So what is this thing useful? How is it useful?
For molarity, it's useful because when you make up when you make a solution, you have to know the concentration. So anytime we're dealing with a solution, we have it in a concentration. So you have to know how it's made. So for me, whenever I am making up a lab, and it tells me, okay, they're going to need, you know, I'm going to need a liter of 0.25 molar solution, so I have enough for everybody. I have to go in there and calculate, well, how do I make that up? Because most of the stuff we buy as the crystals, because it's easier to store, and I can buy 500 grams and make a whole lot of solution out of that, as opposed to buying the solutions. It gets very expensive, okay? So molarity, I definitely use way more, okay? Molality is going to be used when we do colligative properties tomorrow, because I can figure out, I can figure out a molar mass if I was to put some unknown solution and figure out the freezing point. I could figure out the difference in the freezing point. I could figure out the molality, and then I could back calculate and figure out a molar mass. Okay, we don't do that as often. We don't do that at all in regular. Okay, so that's why. But this is actually, concentration is something I use every time I'm setting up a lab that needs solutions. Yeah. Okay. All right. And you can use it in solution stoichiometry, because stoichiometry doesn't go bye-bye. All right, so the next example, I think, for you says, how many grams of calcium chloride must be dissolved? Is that your next example?
Yeah.
Okay, cool. We're on the same page. So how many grams of calcium chloride? We're going to make 350 grams of a 1.75 molal. And what are we dealing with? Calcium chloride. Okay? So, similar concept. I'm going to take my 350 grams of calcium chloride. No, that's the solvent. I'm sorry. Yeah, sorry. I'm going to start with my 1.75 moles of calcium chloride over kilograms of solvent. And I'm going to multiply by my solvent, which is going to be 0.35 kilograms. Because I want kilograms to cancel out, right? That's over 1. Now I have moles of calcium chloride. So how can I get to grams? Times it by its molar mass. See how useful molar mass is? Isn't it great? So 40.08 plus 70.9 for chlorine. Get 110.98 grams of calcium chloride as its molar mass. So now throw all that in your calculator. And we need, I believe, 2 sig figs from the 350 grams. So 68 grams of calcium chloride would be needed to make that solution at that concentration and that volume. Okay? And then the second question says, I'm going to do it down below. What is the second question? What is the molality? If you take 43.7 grams of sodium nitrate and dissolve in 750 milliliters of H2O. So our solvent is water. Obviously, we're dissolving it. So what's our kilograms?
0.75.
Huh?
0.75.
Because 750 milliliters is the equivalent of 750 grams, which is 0.750 kilograms. And that's because the density of water is 1 gram per milliliter. Okay? So we're going to take the 43.7 grams of sodium nitrate, and I need it to be in what?
Moles.
Moles. And how do I do that?
Divide it by its molar
Divide it by its molar mass.
mass.
14.01 plus 3 times 16. Whoa. 85? 22.99. That doesn't seem right. Plus 14.01 plus 3 times
Yeah,
16.
That's right.
Okay.
8.9.
85 grams per mole on top. So I've got rid of grams. I'm in moles on top is what I need. So I'm going to divide by the 0.75 kilograms. Now I've got kilograms on bottom like I need. So 43.7 divided by 85 and then divide by 0.750. So I get 0.69 molal of sodium nitrate. Okay? Everybody with me so far? Do what? What? This is honestly really all about units. If you can keep up with your units, you can actually, but you have to remember that molality is moles per kilogram and molarity is moles per liter. If you can remember that, you can manipulate the information they're giving you to get what you need to get to. Okay? All right, so that brings us to concentration of solutions, which is in both packets just to keep it fun. Because it came in order, so I just printed those pages that we were missing. So I don't care which packet you do dilutions in. Yeah, it's going to say dilutions. So you can either do it in the packet that we're still in, or you can go back to the other packet. I apologize for my mistake. I hope you will forgive me. Okay? So the dilution concentration, big M, we're dealing with molarity, and V is volume. So M1 and V1 are your initial concentration, your initial volume, and M2 and V2 are your final. Your M1 will always be bigger. You can take that to the bank. There are no exceptions to that, because it's your concentrated solution. And Thomas, earlier you asked why is this important? This equation is important because when we purchase acid, it comes in big jugs of concentrated acid, and then we dilute down what we need. Okay? And so this is something else that I use a lot. Yes, except you always do as you ought to, add acid to water. Don't close your eyes. You always add your acid to your water. Remember that from the safety unit in the very first? Always do as you ought to, add acid to water. You never add the water to the acid. No, it's because it's dangerous. Yeah. It generates a lot of heat, and so if you are putting the acid into the water, it could splatter and hurt you. Yeah, always add acid to water. You can remember it as, I like that saying, do as you ought to, add acid to water, or you could say aw, A-W, acid to water. No. Okay, but this is sodium chloride, so it doesn't matter. We can add anything we want to whatever, okay? So how would you prepare 485 milliliters of a 0.39 molar solution if all you have is 1 molar solution? Okay, the bigger one is always M1. Take that to the bank, people. So that means this has to be M2, so that goes with it, so that's got to be V2. So basically, how much of the 1 molar are we going to use is what we're calculating. So we're going to be solving for V1. So V1 is going to be equal to M2 V2 over M1. So plug and chug. Incidentally, because we're going to be canceling out our molarities, you can go ahead and leave it in milliliters. You don't have to go to liters if you don't want to. So 0.39 molar times 485 milliliters over 1 molar. So my molarities cancel out. 189 milliliters. But we're not done because it says how would you prepare? So what I would do is I would take 189 milliliters and add enough water to equal 485. So basically I would add 296 milliliters of water, okay? Do not say that you would take 189 and add 485 to it, because now you have a different volume. Your final volume needs to be 485. So you would add 189 milliliters of water and then add enough water that you finalized at 485. You wouldn't add 485 to it. Does everybody get that?
And that would be called a solution.
That would be called a 0.39 molar solution, yes. Okay? Provided the 1 molar solution was made up correctly. You got to trust that it was made up correctly. I do dilutions all the time, like all the time. Okay? It's easier to make that up than the solid sometimes. Okay? So that's how you do dilutions. Now we have 2 more and then we are done. And that is percent solution. This is in the supplement. Okay? How do you find the percentage of anything?
Times about 100.
Part over whole times 100. Okay? So the mass percent is your mass of your solute divided by the mass of the solution. Now, if this solution is going to be your solute plus your solvent. So you got to have both masses, okay? Because you're adding them together, okay? This is not chemistry, what we're fixing to do. This is good old-fashioned Algebra 1, solving for an unknown, okay? Wants to know how many grams of sodium chloride would be required to make a 10% solution if you had 50 grams of water. So 50 grams of water is obviously your solvent, okay? So we're going to plug in X for how many grams of solute. So we're going to say X over X plus 50 is equal to 0.10. Why 0.10?
Okay, divided by 100.
10 divided by 100, okay? Now, earlier I just went and said what X was, and they freaked out on me, so I'm going to do the math, which is not my job, by the way. I'm a chemistry teacher, not a math teacher, but I'm going to do the math because they freaked out on me earlier when I just said X is equal to that. So, like, okay. So, we cross multiply, and we get X is equal to 0.1 X plus 5. Then we'll change colors.
Why is it plus 5?
Because 1/10
0.10 times 50 is 5 when I cross multiply. So then I'm going to subtract 0.10x from both sides because that's what they taught me many years ago. I don't even know how many years ago that would be. So then I'm going to be left with 0.9, whoops, it's doing crazy things. 0.9x is equal to 5. So then x is equal to 5 over 0.9, which is 5.56 grams of sodium chloride. So I would add 5.56 grams of sodium chloride to 50 grams of water, and I would have a 10% solution of sodium chloride. Okay? Any questions on that? That's not math, that's not chemistry, that's algebra. Okay? So that's mass percent, and then the last one is volume percent, which guess what? Works the same way except with volumes. Okay? So, same thing. Volume of solute over volume of solution. Again, that means we have to do solute plus solvent. Okay? So this is what you would do with solutions if you're mixing a liquid in a liquid, basically. Okay? So like acetic acid is a certain percentage. The isopropyl alcohol, that's the alcohol you put on your bobos when you get a cut. Those like 70% by volume is what that is. Okay? So this one wants to know how many milliliters of ethanol would be required to make 20% solution using 400 milliliters of water. So same concept, X over X plus 400 equals 0.2. Cross multiply, and you get X is equal to 0.2 X plus 80. Change colors so y'all know what I'm doing. So minus 0.2 X minus 0.2 X. So then I have 0.80 X is equal to 80. So X is equal to 100 milliliters. So 100 milliliters of ethanol added to 400 milliliters of water would be a 20% solution. And that, my friends, is the end of today's lesson.